Hello, and thank you for coming to my presentation today. My name is John Bussey, and I'm excited to talk about our work on using Mountain Helens ash as a lunar regolith simulant. This characterization work has been carried out in the Nuclear, Optical, Magnetic, and Electronic Materials Laboratory here at Washington State University. So in trips to the moon, such as the upcoming Artemis missions, one key issue, one thing that needs to be tested is compatibility with lunar regolith. Lunar regolith is destructive, hazardous, and toxic to human health and equipment used. And so trying to figure out ways to mitigate this dust hazard, such as on spacesuits and in the airlock and on solar panels, as well as compatibility with things such as rovers and landers, is absolutely critical. Unfortunately, current supplies of simulants are limited, especially commercially, and require intensive, onerous processes to make them and sources as far away as Greenland. Fortunately, Mountain Helens ash occurs naturally and without modification, and it has been stored in Pullman, Washington, where it has not been weathered or exposed to the elements at all. We hypothesized the volcanic ash from Mount St. Helens would be similar to lunar regolith, since both are formed in high and extreme circumstances, such as temperature, pressure, and erosion, such as volcanic explosions and meteoroid impacts. So we looked at a variety of important factors, such as the ones deemed most important, which are really mineralogy, particle size distribution, and morphology, with agglutinated characteristics also relevant. We looked at these on a variety of different characterization tools, including scan electron microscopy, X-ray computer tomography, among others. And overall, we found that this Mountain Helens ash is fairly similar to the feldspathic Helens dust and regolith, and that it could create a fairly promising simulant. So when thinking about the mineralogy, both have significant amount of glassy phases, where the Mountain Helens is about 80% of those glass, breccias, and agglutinated particles, while only 20 to 50% for lunar regolith. That said, they both contain a significant portion of these particles. They also have significant amount of crystalline phases, which are mostly plagioclase feldspar. It's a bit smaller for the Mountain Helens ash, but again, it's more of the calcium and sodium over potassium. Both are similar to an orthosite, with lunar regolith being in the Highlands region being entirely anorthosite. Both also have agglutinated particles that are mostly vitric. And this was determined both in the literature, and we worked on this with X-ray diffraction, energy dispersive X-ray spectroscopy. Additionally, the morphology is a really critical character, especially for mechanical testing, because you need to know how these particles interact with bearings and joints. And so what we were able to find with scan electron microscopy is that there are high amounts of both angular particles, as you can see up top with these little shards, particles that have fused surface. So in the second from the top, you have these particles with lots of small pieces that are fused to the surface by the high extreme heat and pressure, blocky mineral fragments, and pieces of glass that are very glassy with fused pieces on top. And these were exhibited in both lunar regolith and Mountain Helens ash. Here on the bottom, you can also see that we have things very similar to agglutinates, where you have these kind of crystalline lithic fragments fused together by glass with big pores on the left, and a glassy piece with fused lithic particles on the outside. And on the inside, you have this glassy matrix with crystals that have come out of it. Additionally, the particle size distribution is similar. So here you can see in the blue line, you can see the Mountain Helens ash, which rolls right between the average for lunar regolith and the average for lunar dust simulants. And this is really important because it has both some of those really small particles that can get into cloth and into bearings, can be really destructive, as well as some of the larger one that may exhibit more bulk mechanical properties. So generally, we found that Mountain Helens is a low to medium fidelity simulant that is applicable for testing in the lunar highlands. And this is especially relevant because that's going to be the Artemis landing site. There's comparable mineralogy, as you see on the left, even though there's a bit more glass in the regolith, in the ash than in the regolith. Additionally, there are agglutinated particles, which are really rare and difficult to find on Earth. There are whole companies that are designed just to make these particles, and it's really onerous to make. It's particularly notable and special that we can find this in the Mountain Helens ash. Furthermore, the particle size distributions are the same, or not the same, are similar, falling kind of between dust and lunar regolith. And so generally, it's pretty well aligned for mechanical testing, not so much for chemical testing, but where you're testing the compatibility and whether the survivability of and the durability of proposed technology. This simulant works really well, as for dust mitigation methods. And further work is needed to kind of figure out some of maybe the best way to apply Mountain Helens ash, but generally we found that it is a promising low to medium fidelity simulant. So thank you guys for coming to my talk today, and please let me know if you have any questions or anything you want to talk about further. And I really appreciate being here. Thank you.